Welcome back to the Explainer. Imagine this. You're standing right in front of a locked switchboard door down in a humming engine room. Behind that steel panel is the exact board deciding if this ship sails or if it just sits dead in the water. I mean, literally every amp, propulsion, thrusters, hotel load, it all flows right through here. But before you can do anything, before you run a single test or start your maintenance cycle, your very next move depends 100% on reading the nameplate correctly. Let's unlock that door and look at these specific ABB medium voltage breaker models you're actually going to run into out there in the fleet. Model ID first, procedure second. I really want to emphasize this right off the bat. Before you even think about touching a single test point with your meter, you've got to know exactly which breaker family you're dealing with, because literally everything else cascades from that one piece of information. Your test procedure, your spare parts strategy, and even the arc extinction medium working inside that sealed unit, they all completely depend on whatever model is stamped on that nameplate. If you get the ID wrong, you're just flying blind. And honestly, in medium voltage marine applications, that's a risk we just can't take. Okay, let's dive into this. 5 ABB ACS models cover the vast majority of the marine fleet. We've got 3 that use SF6 gas for arc extinction. There's the HD4, which is currently in production, and then the legacy HA3 and HPA models, where production has officially ended. The HPA, by the way, is a unit you'll see a ton with those older MHS switchboards. Then, moving away from gas, we have the modern vacuum technology. That gives us the VD4 breaker, using a highly efficient vacuum interrupter, and the V-contact vacuum contactor. Both of those vacuum models are fully under production today. So it's really just 5 models, but identifying them right away tells you exactly what you're up against. Now, what's really interesting about this slide is the pattern it reveals. It totally splits your operational reality into 2 very distinct worlds. On one side, we have our currently produced models, right? The HD4, VD4, and the V-contact. If you're working with these, you're dealing with fully supported modern gear. Spare parts are usually just a quick purchase order away. But on the other side, you have the legacy hardware, the discontinued HA3 and HPA. Finding one of these legacy tags on a vessel, that instantly shifts your job from routine maintenance to strategic obsolescence management. You're not just a technician at that point, you've got to be a forward-looking planner. Taking a step back for a second, this whole split perfectly illustrates a massive shift in the broader industry. The modern marine trend is this decisive, deliberate move straight toward vacuum technology. Honestly, if you are commissioning new build tonnage today, you're almost always going to be working with vacuum technology instead of SF6. Vacuum interrupters, like the ones in the VD4, are super efficient, quick opening, and essentially maintenance-free. Meanwhile, SF6 gas, which, has amazing heat transfer properties but needs really careful handling because of those sour-smelling decomposition byproducts after an arc, well, it's hanging on only in the HD4 model as far as current production goes. The industry has clearly spoken, and vacuum is the standard moving forward. Okay, let's anchor these technical specs to physical reality for a minute. Put yourself in the shoes of a commissioning engineer. Let's do a quick check. Say you're on a 20-year-old platform supply vessel, and you've just been told, hey, we need spare poles for an HA3 breaker. What is your realistic sourcing plan here? Remember, you can't just call up the factory and order brand new parts off the standard assembly line, because as we just established, HA3 production ended a long time ago. So how exactly do you keep this vessel operating safely without causing massive downtime? And this brilliantly illustrates why you absolutely cannot assume indefinite spare support. Your realistic plan requires a serious pivot. First, you're going to check ABB's legacy parts channel just to see if there's any remnant stock floating around. Second, you start scouring the secondary market. But the absolute most critical step, you immediately start budgeting and planning for an eventual VD4 vacuum retrofit. The end game for a legacy breaker is always going to be a modern upgrade. The very second you spot that obsolete tag, your whole strategy has to shift so you can guarantee the long-term reliability of that vessel. So, the crucial point is this. By fully internalizing this breaker family tree, you can walk into literally any switchboard room and instantly judge the obsolescence risks right on site. You now know the 5 major ABB medium voltage models by name. You instantly recognize which ones are currently produced versus the legacy ones. And most importantly, you know exactly how to formulate an informed spares and retrofit strategy on the spot. You're taking what could be a total logistical nightmare and turning it into a smooth, planned engineering upgrade. But identifying the equipment from the outside, that is really just the beginning of the journey here. Sure, you can read the nameplate, you spot that legacy HSA breaker, and you know for a fact it relies on SF6 gas. But do you know exactly how its internal puffer mechanism violently snuffs out a superheated electrical arc in just milliseconds? Think of it like a high-powered bicycle pump. It compresses the gas and blasts it directly onto a separating contact to just completely kill an arc instantly.
It is a wildly fascinating piece of hardware mechanics, and actually, that is exactly what we're going to tear apart in our next case study. We're going to take one of these models apart completely, get deep inside that metal-clad cubicle, and see exactly how SF6 extinction happens inside the real hardware.